Alright, I am making another video. I didn't plan on doing this, but I'm making another video on this to follow up on this my previous video on this Lafayette model KT92 kit tube amplifier. And I had just completed this project by replacing the caps and a whole host of other things to get it running and revive it from the trash bin. And during my last video I discovered some amazing distortion in the bass regions, in the bass frequencies, that I didn't notice before, because I was taking distortion measurements using the standard 1 kilohertz, and with this amplifier I wasn't paying too much attention to it because it's just a little kit amplifier that I just wanted to get running. But at any rate, when I was checking the frequency response, I noticed this weird bass distortion that only occurs in very low frequencies. And something occurred to me. One of the things I had to do to get this amplifier running at its lowest distortion possible while measuring it at 1 kilohertz was to remove or eradicate the negative feedback. Let me get the schematic. And because for some reason the negative feedback was adding to the distortion spectrum, so I ended up looking at the schematic. I had to hit pause there for a second. I had to sneeze. My room is, my workshop is dusty, and I ended up getting allergies down here. So the negative feedback extends from the positive 8 ohm tap output on the output side, or the secondary side of the output transformer, and it comes all the way back down to the cathode resistor of the input 12AX7, which is normal. That's cathode feedback, and it is negative feedback, even though we're taking the signal from the positive side of the output transformer. It is negative feedback because, well, I won't get into why, but when you feed it back to the cathode of the cathode resistor of a tube, you end up raising the voltage of the cathode with respect to the grid, which is the same thing as lowering the voltage of the grid. And this is an inverting amplifier. The output is inverted relative to the input. So at any rate, so I ended up having to sever the negative feedback in order to improve the distortion, which is odd. Now again, normally negative feedback with a tube amp is mostly for purposes of reducing noise that's induced in the circuit because of various sources like AC filaments and many other sources. But it shouldn't. Negative feedback should not cause distortion. It should help it a little bit, but it shouldn't cause it. If it causes it, there's a problem. So the fact that without negative feedback I'm seeing this amazing distortion in the bass frequencies that I'm going to show you in a minute, that might be the result of the problem I was seeing, and the reason I had to sever the negative feedback to get this thing to work. So somewhere in the circuit here, and now right now we're dealing with an open loop circuit that has no negative feedback, and I'm still seeing distortion in the bass region. So that distortion being created somewhere here and then being fed back was causing some other problems. And I think if I can find the source of that distortion, I might be able to reintroduce the negative feedback and actually improve the noise. So that's my goal here. The first thing, this is a classic troubleshooting situation. The first thing I want to do is figure out which one of these components is causing the distortion. So let me do a recap of what the distortion looks like. Turn out my light here. I've got a signal being applied right now. It's 108 hertz because we're only dealing, the only time I see the distortion is in the bass frequencies from 20 to about 45 hertz. And so I'm inputting 100 hertz right now, and I'm tapping. I've got one oscilloscope lead directly across the 8 ohm dummy load, which is equivalent to being across like the speaker. And I've got the other oscilloscope probe directly to the input. So we're going to see the input signal compared to the output. In this case, looking at the scope, the input signal is yellow and the output signal is red. Now, so far at 100, we are at 108 hertz. RMS of the output is 1.7. Let me actually lower that some, 1.7 volts to about 1 volt, to give us about 1/8 of a watt, because I don't want to look at any distortion that's caused by just exceeding the power rating. So 1/8 of a watt at 1 kilohertz, I know had a 0.7% THD, so we're good there. Now, let me start lowering the, now watch the red. I'm going to start lowering the frequency, and now at about 50 hertz. Now, I don't know if you can see that in the red, but now again, the yellow is the input signal, nice and clean, and the red is the output. You can see something weird start happening. There's a lump in that sine wave. Now, when you can see distortion on a sine wave, it's severe. Now we go down below 50. Now I'm down to about, let me go to 30. Oh, look at that. That's awful. You can really see that sine wave. It's starting to look like a triangular wave almost, and you can see a lump. Let me bring this out a little bit. You can see, in compared to the input, nice, clean, perfect sine wave, you've got this little lumpy area. There's some kind of harmonic that's being added to the trailing edge of that sine wave. I have no idea where that's coming from, but I want to figure it out. Let me go down to 20, 24 hertz, and you know, you can really see it there. There we go. That's awful. That's a terrible output sine wave. Only happens below 50 hertz. Look at that. Now, somewhere that distortion is being introduced, and it's got nothing to do with the negative feedback, because I don't have negative feedback right now. It's got nothing to do with the tone controls, because those have been disabled. So it's somewhere in one of the. I'm going to trace the signal from the input through the input to the inputs of the 12AX7, and then to the inputs of the output tubes, which should be phase inverted on either side. And if things look good there, then I'm going to look at the output, or I should say the input, the primary side of the transformer. And I suspected in the last video that this was being caused by the output transformer, and I still think that's going to be the case, because this circuit, all this circuitry here is standard stuff, and I don't know if a bad tube could cause that, but I seriously doubt it, because it's frequency dependent. It only happens in the bass frequencies, and it doesn't look like something that a capacitor causes or a tube causes. It looks like some weird effect that's being induced by the transformer, maybe by some weird magnetic effects or some winding. I mean, now, granted, an output transformer, the primary side is nothing but a choke or a coil, but I just have never seen this kind of distortion before, and haven't come across it, so I just don't know. But given that the way a transformer works, and the magnetic fields involved, and the coupling between the primary and secondary side, and the reflecting back of voltage or of impedance, that sort of thing, weird things can happen, and that's where I suspect it's going to be. So let's start the process of tracing signal and figure out where the problem is. Now, the reason why I'm doing this video is I realized I've actually got another transformer I might be able to use, and it's if it turns out to be the transformer, I'll get to that, cross that bridge when we get there. But if it turns out to be the transformer, then I've got to figure out what the turns ratio of this transformer is. It's a push-pull transformer, so I need to get a push-pull as opposed to a single-ended transformer. And I got to figure out what the turns ratio is. And then, knowing that, I should, I've got a couple of those laying around, and I might be able to substitute another transformer for this one and see if that that distortion goes away, and then maybe reintroduce the negative feedback and see if that cleans up the noise. So this is a classic troubleshooting, and I did this. The amp actually sounds good as it is, but I don't like these circuits getting the better of me, and I just realized yesterday again that I had this distortion, and if everything went according to plan in terms of restoration, then I'd never learn anything. So I'm going to dive back into this little amp and figure out the problem and try to get it fixed, just for the experience of it, I guess. And I thought it might be helpful to somebody to do a video. I have no idea, but I'm doing it anyway. So start the troubleshooting process. First thing I'm going to do is I'm going to leave on my scope the red signal, which is the voltage across the 8 ohm dummy load, the speaker substitute. But that yellow trace I have here, I'm going to take my probe and just start putting it from the starting at the input, and just start putting it in various places and finding out, when we go from a clean sine wave to a dirty sine wave, figure out, that's the component, that's the problem. Maybe it's the output tubes. Well, fortunately, I do have some additional output tubes. These are 35C5 tubes, and I do have a couple of those laying around. But I did test these tubes on a tube tester, but that doesn't tell the whole story. So let's start the tracing process. All right, right now, my yellow trace probe is, I jumped right to the output of the first 12AX7. These 12AX7s are just great tubes, and I just can't imagine the 12AX7 causing this. So my probe is actually right, right here. So pin 6 of the first half of the 12AX7, and things look good. That is a nice, clean sine wave, the yellow trace. Again, the red one is across the speaker. And so the first stage of amplification, this half of the 12AX7 is doing well. So the second half of the 12AX7 actually acts as a phase inverter. Doesn't do any amplifying per se. What should come out of the second half should look like exactly like that yellow one, except 180 degrees out of phase. So let me go ahead and test that one. Looks good. So the output of that one's good. So I'm going to take my probe and go to the inputs of the 35C5 power tubes, output tubes. So I'm going to start out with pin 3 of this guy, and then go look at pin 3 of that guy. Make sure everything still looks good. The only thing between these two is a capacitor, but there is a divider network here, so I don't know let's give it a shot and make sure the inputs are looking good there. Okay. Yeah, well, you know what? I'm on pin 3 and I'm getting a weird signal, and I think I got a bad connection. Let me try that again. Okay, I said pin 3, but it's actually pin 5, and I'm there now, and that looks good. So our input to this half of the push-pull pair at pin 5 on the grid looks good. I'm going to go ahead and test the other tube, make sure that looks good. Alright, the other half, the input looked good, so now I've got my probe at pin 7, which is the connected directly to one half of the output transformer, and I'm getting something weird. Things do get kind of squirrely on output transformers because of how it acts as an inductor, but I haven't seen anything like this before. Looking at the yellow trace, now there's that little hump. I think that might be correlating. Again, there's a phase reversal through the transformer, but it might be correlating with that thing right there. I don't know what that little hump there is. It might be canceling out and then the push-pull effect of the transformer, but I'm just not sure. But that's not exactly a clean sine wave that's going through that. That's on the plate of the output tube, and I'm not sure what's going on. But one thing I'm going to try. Oh yeah, okay. What I want to do is at this point. So we're looking at the plate of one of the two push-pull outputs. I'm going to go ahead and increase the frequency. We're at 17 hertz now, where this is problematic. So I'm going to increase the frequency to 100 hertz, where we know there's no problem. And so you can see that now we have a nice clean sine wave. There's some things bouncing around there, but again, these when you're looking across an output transformer, you get some weird effects due to the inductance, but it's still a nice clean sine wave, even though it's kind of hobbling around. I'm not sure what's causing that. There's some kind. It's being modulated somehow by something. But and again, I have no negative feedback hooked up right now, but still, it's a clean sine wave, even though it's being modulated. It's definitely being modulated by a really low frequency. Let's see if you can. Yeah, you can see when you do that, you know, there's some modulation going on, but it's still a clean sine wave. So that's accounts for why you know, we're not seeing this. Let me go back to the lower frequencies. Back to 30. 35 hertz. And then it starts looking really ugly. We're at 32 hertz right now. So that's really ugly, the yellow trace. So what happens is each of these push-pull are producing that ugly signal out of phase and anti-phase, and so there are certain harmonics that are going to cancel out, and then and some of them won't cancel out, and then some of them might be additive. But so across the output, the secondary side of the transformer, we see this horrible red sine wave with this hump in it right there. And given that there's no negative feedback, we have an open loop circuit, the only thing that could be causing it that I can think of, well maybe it's, I doubt it's an inherent characteristic of the 35C5 tube, because that is an audio output tube. So it's probably not inherent. Oh, maybe one of the two tubes is bad. First thing I'm going to do is substitute some new tubes in there, some new old stock ones that I happen to have. And if the problem persists, then what's left is the output transformer. And I'd like to you know, put one on the bench and sub it in there and see what the results are. And I have one I can use for that. So first I need to determine the turns ratio of the transformer, and then sub in another transformer and see if we have the same results. I seriously doubt we will. So that's the next step. Actually, the first next step is changing the output tubes and see if we have the same result. That's what I'm going to do right now. Okay, let me see if I can find these tubes. They are 35C5s. Let's see. A couple 12AX7s. That's a big, I don't know what that is. 7591. That's a Chinese tube. 35C5. 35C5. Now the neat thing, I got some old junk amps down here, but this one here, I had this sitting around for a little while, and it's got a bad tube in it, but this one has what I believe to be a push-pull output transformer, and it looks to be the right size for the Heath kit. I've also got these are push-pulls right here, but they are way too big and heavy. They're really big. Too big for the Heath kit. It wouldn't even fit. So I think this is a push-pull. It's got on the secondary side, it's got two wires, and on the primary side, it's got 3. And the red wire, which is standard for the power, which goes to the center tap, is definitely going. It's tapped into the right into the electrolytic cap, so that's the power. Then the other 2 wires, one goes to one output tube, the other goes to the other output tube. So that's a push-pull. The question is it going to give me the same turns ratio I need, or something close? And that remains to be seen. So let me go ahead and pop these new output tubes in, and then give it another test. I expect the same results. I don't think it has anything to do with the tubes, but it's an easier thing to test initially than to start tinkering with the output transformer. So just want to rule this out. Okay, so I put the replacement or the substitute output tubes in there, and I'm getting the same kind of squirrely result. I don't know if that looks. I'm at 32 Hertz, which is where I left off, and it actually looks better. I don't know why. I mean, it's still wobbling around, but yeah, I still see something there. Yeah, there's still a little hump, but the output, it's funny that the output, the red looks better with the new tubes in it. So let me bounce around in frequency. Okay, let me go back up to our 100 Hertz where we had that nice clean sine wave, and the output red, it's across the dummy load, looks good. Still being modulated by something. Still being modulated by something, but that's okay. It looks good. Okay, now let's go back down to the problem frequencies, like somewhere around 30, 20. I'm at 12 right now, but 25. And you start to see that there's some kind of distortion there. It's not nearly as bad, but looking at the red output. But yeah, it's still something going on. There's still something weird going on. I'm moving the tubes around right now, just touching them and kind of moving them to see if anything happens. I checked all the connections. I didn't find any cold solder joints, and nothing's happening. So replacing those tubes kind of improved things, but not totally, not sufficient. This is still for 25 Hertz. This is still really, now we go, it's getting worse. Maybe the tubes have to heat up. Yeah, it's really bad. Okay. Ooh, that's awful. Looking at the red output, that's 13 Hertz. Not that there's anything going on down there, but let me go up to 40. 40 looks pretty good, and before 40, it's still not a pure sine wave. Now at 30, and you can see in the output sine wave. Now we got this other little thing happening over here that's Something's going on. I'll tell you what, just for the sake of I'm turning the volume up now just to see what happens when you change the level. It's still there. That is weird. It's actually improved but not perfect, and so what I'm going to do, just for the exercise of it, I'm at 14 hertz there. Even at 14 hertz, an audio amplifier, you know, even though there's no music energy there really, not a lot, an audio amplifier should still produce a clean sound wave, and sine wave. So I'm going to go ahead and I'm going to measure the turns ratio, and I won't show you that painful process, but essentially I'm going to pull the tubes out right here so that there's no longer a connection to the secondary or to the primary windings, and input a voltage across 1/2 from the center tap to one side. I'm going to choose 1 kilohertz. Put an AC voltage on, and then you measure, you know, you pick a value like, you know, I don't know how many volts, but and then measure the like 10 volts, let's say, RMS. I'll start out with a lower voltage though, and then you measure what comes out of the secondary, and then so for example, if you put in 10 volts and you get 1 volt RMS out across the secondary, then you have a 10-to-1 turns ratio, and I want to find that turns ratio as close as possible. Doesn't have to be exact, but the more you deviate from the design value, the less efficient the output transformer is going to be in terms of delivering power to the load, which is the speaker. But you can get close, doesn't have to be exact. So I'm going to do that now, and I'm going to figure out the turns ratio of this transformer, and then go over to this junk one here and figure out its turns ratio and see if it's anywhere close, and I hope it will be. So that's the next step in the troubleshooting process. But if it turns out that this transformer works, I'm going to see if it'll fit and actually replace this one. And if everything looks good at that point, then I'm going to reintroduce negative feedback, see if that improves the noise and maintains the low distortion. And that way I'll get this amp back to more than 100% probably. But I still suspect there's a problem. It's either, maybe it's just a really junk, cheap output transformer that's just not capable of linearly producing bass frequencies, but I just doubt that. I think there's an internal problem with it, and I'm not sure what it is. It's beyond transformer design. I know how to design with transformers, but in terms of the equations and how the magnetic flux operates and what could possibly go wrong with them, I don't know. Beyond the scope of what I even care to figure out. But so that's the next step. Turns ratio, figure out if this transformer will work, and then actually substitute it in there on the bench first before I disconnect this transformer from the chassis. Just do it on the bench and see if our results are improved. So that's the next step.